So today we will be seeing the Caley-Hamilton theorem. This topic is covered in linear algebra in many undergraduate courses. The proof, however, seems to be involved. Today we will be discussing the theorem, and we will be seeing a proof which you could reproduce in your examinations or for your discussions. Now let A be a P by P matrix with real or complex entries. P is a natural number, and so this is a square matrix. We will be talking of only P by P matrices in this lecture. We know that the characteristic polynomial of such a matrix of A in the variable lambda is given by determinant of A minus lambda times identity, where I is the P by P identity which will be used in this case. Normally, one sets this to 0 in order to find out the characteristic values, or also called as eigenvalues of this lambda, which are the roots of the equation that results. But at the moment this is just an expression. Lambda need not be the characteristic value. Let us see an example of a characteristic polynomial of a matrix A. So let A be equal to 1, 1 upon 4, 1 upon 4, 0. So here A is a P by P matrix where P is 2. P is 2. So this is a 2 by 2 matrix. Let us try to find out what is determinant of A minus lambda I. That would be the characteristic polynomial of this A in lambda. Determinant of A minus lambda I equals one minus lambda 1 upon 4, 1 upon 4, 0 minus lambda. This would result, because this I has only 1 with the diagonal as diagonal entries and 0 elsewhere. So therefore, you simply have to subtract a lambda from the diagonal members of A in order to get A minus lambda I, and then take the determinant of this. Let me try to simplify this. Therefore, determinant of A minus lambda times identity would then be equal to 1 minus lambda into minus lambda minus 1 upon 4 into 1 upon 4, which would then simplify to lambda squared minus lambda minus 1 upon 16. Notice that I am not equating this to 0. So this is the characteristic polynomial of A in lambda, the characteristic polynomial of this A in lambda. That turns out to be this. So this is a quadratic expression. As a polynomial in lambda, it has degree 2. The coefficient of lambda to the power 2 is non-zero, a real number or a complex number in general, and there are no higher powers of lambda. So you can define a degree of a polynomial as the power of lambda, the largest power of lambda having a non-zero coefficient, a complex coefficient in general. So by that definition, this has degree 2. The coefficient turns out to be 1. The coefficient of the largest power of lambda turns out to be 1. Now let us make a curious substitution. Instead of lambda, we pretend that we have the matrix A instead. Of course, that would be a matrix expression, a P by P matrix. That's what would result. Suppose I decide to do that. Let us see what happens. A squared minus A minus 1 upon 16, and since I don't have anything here, I earlier had 1 there, or lambda to the power 0 here, I would say I have A to the power 0, and A to the power 0 is identity matrix. So let me put the identity matrix here. This is what would result. Of course, this itself is a matrix, P by P. This is a P by P matrix, so is this, and so is this. So this whole thing would evaluate to a P by P matrix. We call this the characteristic polynomial of A, which gave you these coefficients, in A. Instead of in lambda, I say in A. So the whole thing, instead of being a scalar or a number, technically we call it a field member. Instead of that, it turns out to be, the polynomial turns out to be a matrix, a P by P matrix. So the characteristic polynomial of A in A turns out to be a matrix, a P by P matrix. Now let us try to see what that evaluates to. Since we know we have taken an example of A, let us see what this evaluates to. So I need A squared first. So in our example, A squared will turn out to be, if you look at this A and multiply it to itself, like 1 and 1 upon 4 multiplied to the column 1 and 1 upon 4. So the product would be 1 into 1 plus 1 upon 4 into 1 upon 4. That I would put in the first place. So I'll have 1 plus 1 upon 16, or 17 upon 16. Similarly, the second entry in the first row, 1 and 1 upon 4 multiplied by 1 upon 4 and 0. So I have 1 upon 4 into 1 and plus 0. So I have simply 1 upon 4 plus 0 as the second entry. Let me put a comma to make things easy to understand. Similarly, 1 upon 4 and 0 here multiply 1 and 1 upon 4. So I would have 1 upon 4 into 1 plus 0 again, comma, and the final element 1 upon 4 0 multiplied to 1 upon 4 0. So that would be simply 1 upon 16, let me write this dialectically, plus 0, which gets simplified to 17 upon 16, 1 upon 4, 1 upon 4, 0. So I have A squared. Let me substitute this A squared in this polynomial, matrix polynomial, to obtain the following. Therefore, A squared minus A minus 1 upon 16 times identity equals 17 upon 16, 1 upon 4, 1 upon 4, 0, minus A, which I already have here, let me write that down, 1, 1 upon 4, 1 upon 4, 0, and finally minus 1 upon 16 times identity. I could take that 1 upon 16 inside and have this kind of an expression, 1 upon 16, 0, 0, 1, 1 upon 16. So we are trying to evaluate this polynomial. We have everything in place. Let us try to see what happens. 17 upon 16 minus 1 upon 16. You could make use of this if you wish. You get a 0 in the first place. Similarly, 1 upon 4 minus 1 upon 4 minus 0. Again, you would get a 0. 1 upon 4 minus 1 upon 4 minus 0. Again a 0. And 0 minus 0 minus 0. There was a, I think there is a mistake here. Yeah, this is 1 upon 16. Sorry, I should have written this as 1 upon 16. Yeah, sorry. So the A square matrix stands corrected. I had put a 0 earlier. It's actually 1 upon 16, as you can see here. Similarly, this step needs correction. This should be 1 upon 16. Sorry. So it's 1 upon 16 minus 0 minus 1 upon 16. You end up with 0 again. So you notice that you have a square minus a minus 1 upon 16 times identity getting evaluated to the null matrix. I call it the null matrix. Or 0 matrix. If you add this matrix to any other matrix, P by P, you would get the same matrix out. So this looks some kind of a coincidence. This seems to work for this special case of this matrix. In fact, a surprise, it works for all P by P matrices. It works for all P by P matrices. This observation in fact goes by the name Caley-Hamilton Theorem. So take any P by P matrix, find out its characteristic polynomial, and evaluate the characteristic polynomial of that matrix in that matrix, something like this, and that should evaluate to 0. The characteristic polynomial of A decides these coefficients, and in A decides this thing which you write here. Okay, so let me write down the statement properly. The Caley-Hamilton theorem. Let A be a P by P matrix, then the characteristic polynomial of A in A evaluates to the null matrix. Evaluates to the null matrix, regardless of what this A is. It could be symmetric, not symmetric, invertible, whatever. Real entries, complex entries. So this comes as some kind of a shock. Why does this happen? How does this happen? The proof, it turns out that it's a bit involved, and sometimes there are red herrings. You might write down things like determinant of A minus A times identity and try to see whether that is 0, with the inspiration of determinant of A minus lambda I to be being the characteristic polynomial. So if you replace that lambda by A, you might mistakenly think that you would get the characteristic polynomial. That's not really correct. Though determinant of A minus A times lambda I would be determinant of the null matrix, which is 0 itself. That is of course correct. But determinant of A minus A times I is certainly not the characteristic polynomial of A in A. It's basically the determinant of a 0 matrix. That's not the characteristic polynomial of A in A. As it stands, if you substitute that lambda by A, in determinant of A minus lambda I, what you get is certainly not the get on the left is certainly not the expression of the characteristic polynomial of A in A. So erroneously, some people say that this is the proof of Caley-Hamilton theorem. That's really not correct. So how do you prove this? Before you set out on this proof, there are a few things that I wish to develop. So let me go along those. Let us come back to the characteristic polynomial of A in lambda. The expression which you see here is the characteristic polynomial of A in lambda. It's the determinant of a matrix. What kind of a matrix is that of which the determinant is being taken? The matrix is A minus lambda I. This matrix expression, it involves two matrices and lambda, could be thought of as a polynomial in lambda with matrix coefficients. I could say that this is basically lambda to the power 0 A minus lambda to the power 1 times identity matrix. So this is a polynomial in lambda with matrix coefficients, P by P matrices. So lambda to the power 1 has the coefficient minus identity, and lambda to the power 0 has the coefficient A, which you began with. So this is a polynomial in lambda. This is a polynomial in lambda with P by P matrix coefficients. The largest power of lambda having a non-zero matrix coefficient in this expression is 1, lambda to the power 1. It has coefficient identity matrix. So you could say that this is a degree, the degree of this polynomial is 1. We will come to this concept a little later. Another example, lambda square into lambda square times the square matrix P by P. P is 2 here. Lambda cubed into a P by P matrix. P is 2 here. So this is another expression. This is another expression of in lambda with matrix coefficients. The largest power, the greatest power of lambda having a non-zero matrix coefficient here is 3. So this could be said to be a polynomial in lambda with matrix coefficients of degree 3. So in general, let me define T of lambda, script T of lambda equal to d0 lambda to the power 0. You could write lambda to the power 0 before or after the matrix d. d0 lambda to the power 0 plus d1 lambda to the power 1 plus dot dot plus dn lambda to the power n is a polynomial in lambda with p by p matrix coefficients d0, d1 to dn, and we assume that dn is not equal to the null matrix, not equal to 0. So script p of lambda is a polynomial in lambda of degree n. You have this dn not equal to 0 and there is nothing further. So p lambda is a polynomial of degree n in lambda with matrix coefficients, they are all p by p. Let me say the set of all possible polynomials in lambda with p by p matrix coefficients is called S. So let me call this S. S is the set of all possible polynomials in lambda with p by p matrix coefficients. Notice that I am not restricting myself to only polynomials of degree n where n is fixed. No, they could be of any degree, but they should have some degree. So I must also specify here that n is a whole number. W, n is a whole number. So the set of all possible polynomials in lambda with p by p matrix coefficients is called S. I call it S. It's an important set. We will see further regarding this S. But first, let me formally define the degree of a member of S. We have seen what is a degree before. I will just formally define it. So degree of p script p of lambda belonging to S is the power of the greatest power of lambda having a non-zero or non-null matrix coefficient. By power I mean the entire term lambda to the power something. So the whole thing is what I mean by power of lambda, and here I mean just the exponent, or you could say just the exponent of the power. You could use the word exponent here instead. And power of lambda, you could think of that as denoting lambda to the power 3 or 4, whatever. So this is the way it's defined. Okay. So the way I'll be writing my expressions, I'll start from the 0th power and with this coefficient, and coming up to the final power, whatever that is, and the last matrix coefficient would be non-zero. This is how I would be writing down my expressions. Okay. So this is very much like the polynomials you might have handled, where lambda had lambda to the powers of lambda had complex or real coefficients. This is very much like it. Now let us define, like you did for the other polynomials, let's define polynomial addition. So we denote it by plus. So if script p of lambda is equal to d0 lambda to the power 0 plus d1 lambda to the power 1 plus dot 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 plus dn lambda to the power n, and q of lambda equal to d0 dash lambda to the power 0 plus d1 dash lambda to the power 1 plus dot 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 plus dm lambda to the power m. They are both members of S, where all these matrix coefficients are p by p, p is fixed. Then we try to see what is p of lambda plus q of lambda, much like the polynomials with complex coefficients or real coefficients that you use to add. Notice that I have taken m different from n. M could be bigger than n or m could be lesser than n. So let me define p of lambda script p plus script q. Let me use a script q here. Script q of lambda is defined as follows. That also will be a member of S, so that also should be a polynomial with in lambda with matrix coefficients, and that is created out of these two matrices, these two sets of matrices, d0 plus d0 dash lambda to the power 0 plus d1 plus d1 dash lambda to the power 1 plus, as long as you could have entries on both sides. But somewhere you might fall short. Suppose m is lesser than n, then you are going to fall short. You are going to say that, oh, finally I have dm plus dm dash lambda to the power m, and beyond that you are simply going to have sigma over I equal to m plus 1 to n d I lambda to the power I, where I is an index, where only this prevails if m is lesser than n. So m seems to be lesser. This one has lesser number of terms. So you are a lot of leftovers in this first unprimed or undashed summation. So these leftovers have come here. As against that, if you have m bigger than n, and so on and so forth. See, this might even exhaust at 1, but for the sake of example, I've kept it, kept things as, for the sake of depicting something, I've kept it things pretty much not very general. So you would have plus dn plus dn dash lambda to the power n. In this case, you have n is falling short. There are more terms here. This is dash, sorry. So plus sigma over, let's say I equal to n plus 1 to m of d I dash. This time this one is bigger, m is bigger, lambda to the power I, if m is bigger than n. Of course, if m is equal to n, then you will have terms here exactly equal, so you don't have to do all these things. You can simply say that this is equal to sigma over I equal to 0 to m of di plus di dash, or you could say n instead, lambda to the power I, if m is equal to n. The sigma is the summation sign I have used to cut a long notation short, long expression short, sorry. So you see that this goes much in the same way as you would do when you add polynomials with real or complex coefficients. What happens to the degree of this polynomial, of the sum? You note that if m is not equal to n, or m is lesser than n, or m is bigger than n, you'll see that the degree of the sum would necessarily be the degree of the bigger of the two. I forgot to mention here that when I say these polynomials, must note here that dn is not equal to null matrix and dm is not equal to null matrix. So that way dm dash is not equal to null matrix. So that way I have this is a polynomial of degree n and this is a polynomial of degree m. So I should have mentioned that there. So assuming that, you notice that in this case the coefficient of the highest power of lambda here would be n, the power would be n. So dn would come into picture, and that's the coefficient of this sum also. So therefore the degree of this sum would be exactly n, the bigger of the two. Similar in this case, the coefficient of the largest power of lambda here would be the coefficient of power m, because m is bigger than n and it's the last thing occurring here, and the coefficient would be dm dash. That is non-zero because of this. So indeed dm dash would be the coefficient of the largest power of lambda in the summation as well. So therefore the degree of the summation would be the degree of the bigger of the two, bigger degree of the two. But in this case there is a slight catch. The largest power of lambda which you see here is lambda to the power m, but its coefficient, if you try to check, dm and dm and dm dash, or dn and dm dash, because m is the same as n, these two are m and n are the same. The largest, the d here and the d there for that m or n, is both of them individually or non-zero. But if you sum, there is no guarantee that the sum would be non-zero. Okay, so this is much like your polynomials. So this degree, the degree of the sum, would be lesser than or equal to the common degree. Okay, so in general we say that degree of p of lambda, this is the symbol for degree of p of lambda, degree of p of lambda plus degree of q of lambda, deg of p of lambda, q of lambda, is lesser than or equal to max of degree of p of lambda, comma, degree of q of lambda. You could do slightly better. You could do slightly better than this, because the equality holds when these two degrees are not the same. So further you could say, just to capture these statements, equality holds when degree of p of lambda is not equal to degree of q of lambda. So I am putting this for the sake of completeness, but this is what you get. Much the same as what you would have when you have the polynomials, with real and complex coefficients. The equality could hold even when the degrees are the same, but not always. See, this dm plus these are non-zero, so the sum also happens to be non-zero, no problem, but not guaranteed. Okay. So this part is not if and only if. Sorry, this part is if and only if, but okay. One should be careful. One should say that when the equality, yeah. So when degree of p of lambda is equal to degree of q of lambda, that doesn't guarantee that the degree of this is necessarily equal to the maximum of these to the common degree. Not necessarily. That's what one should remember. That's what I meant. Okay. All right. So much about this. So very nice. This first you'll say, okay, I mean this looks like the set of polynomials that we have been dealing with all the time. Well, indeed, this is in fact, if you add, you'll find that this S forms what is known as a group under the binary operation plus. It turns out that this plus is a binary operation. Those who have done a little bit of abstract algebra would be able to follow what I am saying. Plus is a binary operation over S. It's a function from S cross S to S. It's a binary operation. It is associative. Suppose I have three polynomials, p of lambda, q of lambda, and capital script r of lambda belonging to S. I could first add p of lambda plus q of lambda and then pre-add the result to script r of lambda, or I could first add q of lambda and r of lambda and post add the result to p of lambda. Doesn't matter, the result would be the same irrespective of what this p of lambda, q of lambda and r of lambda, what members they are of the set S. So such an operation is said to be associative. Plus has an identity, that means a member of S which when added to any p of lambda in S would produce the same p of lambda back. That would be the zero polynomial. That means the polynomial in lambda which is all zero coefficients. If for lambda to the power 0, it has all the coefficient of that matrix is that power is 0, and all powers in fact is 0. It's basically the zero matrix, null matrix. So this has an identity. It's a member of S. I never said that. Okay, I should make a small change. I include the okay. I should say I should also include the zero matrix, because that way I have said this is non-zero. So p of lambda all along with p by p zero matrix. I should have included that in that set. So that's the S that I'm talking about here. So let me include the p by p zero matrix also in this. So so you see the degree thing doesn't apply to 0, 0. So let me keep it aside. So I've artificially sort of added that zero null matrix to this set S for a reason that I want this to be of a certain kind in this set S. So plus as an identity, it says 0. So now since I've included 0 in it, you'll see if I add that null matrix to any polynomial in lambda with matrix coefficients, you'll get the same polynomial out. Then plus okay. So when I say plus has an identity, that means this one could also say that S has an identity. Members of S have additive inverses. That means any polynomial p of lambda, there will be another polynomial q of lambda, so that p of lambda plus q of lambda would result in the null matrix. Basically, you take this polynomial and take another polynomial with negative matrices everywhere, and if you add all that, you will get result 0. So plus is a binary operation over S that would, if S has the null matrix, it should have, otherwise it would be a binary operation. Plus is associative, it has an identity, of course it should have then 0 matrix, and members of S have additive inverses. So S with this operation plus, obeying this properties, these properties, would be then a group. So S is a group. In fact, it's an abelian group. Much in the same way as you deal with polynomials with real and complex coefficients. So S is a group, abelian under plus. So it doesn't matter if you do p of lambda plus q of lambda, or you start with q of lambda and then add p of lambda to it, so q of lambda plus p of lambda, both would be the same for all p of lambda, q of lambda belonging to this set S. That includes 0 incidentally. So, so such groups are said to be abelian. Again, very similar to polynomials which you handled before. So you say, what's the big deal about this? We already know you simply have matrix coefficient, everything goes through. Now let me come to the next operation that you define on this S. Like polynomials, you would now say, I can multiply polynomials as well. So here too, you can think of multiplying polynomials. Polynomials being multiplied. Now let me assume the same p of lambda and q of lambda which I have defined here. What is p of lambda into q of lambda? How do I define this? You would do something like you do for your usual polynomials. d0 into d0 dash lambda to the power 0 into lambda to the power 0, that is lambda to the power 0. Then d0 into d1 dash lambda to the power 1 lambda to the power 0 plus d1 into d0 dash lambda to the power 1 into lambda to the power 0. So you have two products of matrices for the coefficient lambda to the power 1, and so on and so forth. This is what you do. And instead of collecting all the coefficients of the same power of lambda together, let me keep it as it is, and I would simply write this expression as sigma over I equal to 1 to n sigma over j, another index, sorry, this is 0, 0 to m, 0 to m, and here m, di dj dash lambda to the power I plus j. So now if somebody wants I plus j to be 3, then the person goes over all possible I and j from 0 to m, which would give rise to this 3, and then spell out all the products which stand behind that lambda to the power 3. And that's the way you would need to work if you are interested in writing down the product as simply as powers of lambda with matrix coefficients taken together. Okay, but I'll keep things as they are here. This is multiplication. It's a binary operation. In fact, you'll have to worry about 0. So especially I won't go into the subtlety. If you have 0 there, then simply one of them is 0. So how do you multiply? Will you simply hit 0 null matrix to every coefficient that you have, and of course you will get the 0 matrix out. Similarly, if you hit it from the right, post multiply, again you would get the 0 matrix. So I'm not talking of those subtleties, they are there, you can follow them, but in general this is what would happen. And I'm taking of course polynomials with degree here, but in general also it is true if you have that 0 member. So multiplication turns out to be a binary operation. It's a function from S cross S to S. Take a member of S, take another member of S, do something to them and get another member of S out. And this process is a function. For every pair of members in S, there exists a unique member in S associated with them under this operation, the answer to the binary operation. So this, it turns out to be the case. You can show that separately. It turns out that this is a binary operation, so dot is binary operation. Then dot is associative. Dot distributes from left as well as right over plus this operation. That means you could do things like, okay, first let me tell you what is associative. Again, very similarly, P of lambda dot Q of lambda pre-multiplied to R of lambda, where P of lambda, Q of lambda and R of lambda are members of S, is the same as P of lambda pre-multiplied to Q of lambda times R of lambda done before. Okay, so this works for all P of lambda, Q of lambda and R of lambda belonging to S. One can show this, it's associative, associativity. And then the distribution, if I have 3 members of S, any 3 members, P of lambda, Q of lambda and R of lambda, then R of lambda pre-multiplied to P of lambda plus Q of lambda turns out to be R of lambda into P of lambda pre-multiplied, R of lambda pre-multiplied to P of lambda plus R of lambda pre-multiplied to Q of lambda for all P, Q, R belonging to S. Similarly, if you hit R of lambda from the right, you have P of lambda plus Q of lambda pre-multiplied to R of lambda, turns out to be P of lambda pre-multiplied to R of lambda plus Q of lambda pre-multiplied to R of lambda for all P, Q and R in S. Okay, so that is left distributivity as well as right distributivity. Okay. So this way, then we can show that this turns out to be the plus. So S under plus and dot turns out to be what is known as a ring. So S under plus and dot is a ring. In fact, if this P of lambda and Q of lambda is the same as Q of lambda, P of lambda for all PQ belonging to S, if it happened that way, then we say the ring is commutative. But this ring is not commutative. P of lambda into Q of lambda may not be the same as Q of lambda into P of lambda. The reason being simple, if you have Q of lambda, P of lambda, then what you'd get is di dash or dj dash into di dash here, di, which is not the same as di into dj dash. Matrices multiplication may not commute for all matrices. It doesn't, most of them it doesn't. So therefore this is a non-commutative ring. This is where you find the first difference between the polynomial ring and the ring with matrix coefficients. This ring is non-commutative. Okay, in the second operation, of course. So the dot. So it's a ring. It's non-commutative, and things are studied further. I mean, this ring is studied further in non-commutative algebra. Things are studied, but we won't be needing everything, save a result which I will just mention. What happened to the degree? Because we checked out when you had sum, we applied degree. Why don't we apply degree here as well? So let us see what happens to degree of the product. What could you say about the degree of the product? I'm ignoring the case where you have 0, because 0 multiplied by anything is 0 post or pre, and that right now we are saying it doesn't have any degree. So let's take something which is non-zero, 0 polynomial. So can you say about the degree? P of lambda and Q of lambda, let me assume they are non-zero. So, and the degree of P is n and the degree of Q is m. Should be careful, you should say Q of lambda here. So, the power of amongst the powers of lambda which are listed here, the highest one is m plus n. Let us see what happens to that coefficient, the coefficient of that power. That power, the coefficient of that power will be dn dm dash. Okay, the coefficient of that power would be dn dm dash. So, P of lambda into Q of lambda RHS as lambda to the power m plus n or n plus m as the largest power displayed. Purposely I am saying displayed, nothing more has been written down. The coefficient automatically has to be 0, but let us check this coefficient lambda to the power. Its coefficient, it means the largest power, the coefficient of the largest power is dn dm dash. None of these matrices are 0. I am assuming them to be non-zero. The P lambda Q of lambda are non-zero members of S. So, this and n is the degree of P and m is the degree of Q. So, therefore, none of them is the 0 matrix. You have two non-zero matrices multiplying each other, one pre-multiplying the other. Does that guarantee that the product is non-zero? So, you recall your algebra class. If you have two non-zero matrices, the product need not be non-zero. Though dn and dm dash are non-zero, dn dm dash itself may not be non-zero. We want something which is non-zero. If it had been non-zero, very nice, then you know that the highest power which is non-zero coefficient is m plus n, but then that may not happen. This does not happen in case of your ordinary polynomials. You will see what happens there. The coefficient, the d is simply a number. The di would be a number, a complex number, a real number. J dash would be a real number, a complex number. You multiply two complex, none of them is 0. Obviously, the product is not going to be 0. That's for sure. Such a thing is not guaranteed here. Your matrices. Okay. So, here is the first result. Degree of P of lambda times Q of lambda. See, certainly not more than lambda to the power m plus n. So, it could be equal to or lesser than. So, therefore, this is less than or equal to m plus n. So, that is degree of P lambda plus degree of Q lambda. Deg of P of lambda plus deg of Q of lambda. Okay. Of course, I mean it could happen that the product, these are non-zero, and the product could happen that the product is also non-zero. So, it is possible, but it is also possible that the product could be 0. Okay. So, therefore, you just can't say it is equal to. Okay. So, here you are. Now, this is the first different result which you have. Okay. We will be using this result, though there are other ways, there are ways to bypass using this, but so at this stage I have introduced the ring of polynomials in lambda with the P by P matrix coefficients, along with of course the 0, the null matrix. I have added it separately, the way I defined polynomials for you. Put a dot here. Yeah. Okay, and this completes the theoretical structure, the abstract structure that you would need to address our problem. So, now let me move to the actual problem that we have. So what has all of this got to do with Caley-Hamilton theorem? We discussed the ring of polynomials in lambda with matrix coefficient, p by p matrix coefficients. What has this got to do with the Caley-Hamilton theorem that we are going to work out? This is what we will see in the next part of this lecture. Now the thing that I'm going to apply, so it's things are slightly subtle there. Not much of this won't be important per se for that, but the idea of having a polynomial in lambda with matrix coefficients is very useful, and indeed with some addition that 0 being put there, that turns out to be having a very nice structure, a ring, which itself is very useful. So I did this. So let us proceed to the proof of Caley-Hamilton theorem using this idea of a polynomial of polynomials with matrix in lambda with matrix coefficients. Let's move on. So the proof. I will need to refer to a result that you have been doing in your undergraduate graduate courses. That result is as follows. If M is a square matrix, we of course take it to be p by p, p as natural number, then M into adjugate or adjoint, I call it the cofactor adjoint of M, is equal to determinant of M into identity p by p. This is a result that is separately proven in undergraduate or graduate courses. This is a matrix which is transpose matrix of the cofactors. So with every member of M, you associate a submatrix which is square, of course, by deleting the column and the row of that particular element. That submatrix, you take that submatrix and take its determinant, then multiply it by a suitable power of -1 in order to get what is known as the cofactor of that particular element, which you consider. So for each element there is a cofactor, and you arrange the cofactors by putting them. Cofactor is a number, it's a determinant. So arrange those cofactors in the places where the elements are. So if I take the 2/3 element and find out this cofactor, it's a number, put it in place 2, 3, and create a matrix like that, then take the transpose of that matrix. That is the cofactor adjoint or adjugate matrix. So M times, and why does this become, there's a separate proof for that, it's pretty easy if you see the pattern, but I will assume this result for this lecture. So M times adjugate matrix of M or cofactor adjoint of M turns out to be determinant of M into the identity matrix p by p. That means this matrix is, this result on the right is simply a diagonal determinant of M, determinant of M, determinant of M, and so on. Determinant of M is a number, by the way. So it's a member of a field, okay, or a scalar, real or complex numbers. Okay. We'll be using this result to prove the Caley-Hamilton theorem. Now, this might seem odd, but it's like this is a creative thing in mathematics. You have a result, you try to apply it to various things and try to see. So you could apply this this result pretending that M were A. You started with that A in the beginning. A is a matrix of which you wanted to find out the characteristic polynomial and so on. So let's take that A. I could substitute simply A here and say A adjoint of A is determinant of A into identity. I could say that. Or you could take inverse of A. If A were invertible, then you would say A inverse, the multiplicative inverse. A inverse into adjoint of A inverse is determinant of A inverse into identity. Or you could take the transpose of A or Hermitian conjugate, okay, and things like that. You could take A squared or A cubed and put it in place of M. You could do many things. You could take a squared plus a and put it in place of m and try all kinds of things, and you'll get results. Some of them will be useful to you, some of them may not. Okay. So that way people experimented, and I said, if I can put any p by p matrix created out of a, why don't I do that degree 1 polynomial which I took as an example right in the beginning? So you could try, let m equal to a minus lambda into identity. The lambda is is a variable. Okay, it need not be the characteristic value, any variable. It's a polynomial lambda, we are going to keep it free. It's a degree 1 polynomial in lambda, matrix value polynomial, matrix coefficient, polynomial matrix coefficients, degree 1 lambda. Why don't I take this with some lambda there? Why don't I take this as m? Sure, you could. Let us try to see what this means. So therefore, a minus lambda times identity into adjoint, cofactor adjoint of a minus lambda times identity is equal to determinant of a minus lambda times identity into identity. Now this is a number, please remember that. Determinant is of course a number, it's a member of a field, scalar. This is a p by p matrix, so is this. It's a transpose of a p by p matrix, but also it's a p by p matrix. Transpose will be obviously of the same order if the matrix is square. And this is a p by p matrix, and these are simply diagonal determinants. Notice that this one is something that you remember. If I keep some value of lambda there, it will be the characteristic polynomial in lambda. So this is the characteristic polynomial in lambda. This is the of a in lambda. Let me call this sigma over I equal to 0 to p, from 0 to p, c I lambda to the power I. Simply it's a polynomial in lambda, and I forgot to mention right at the beginning, if you have a p by p matrix, the characteristic polynomial turns out to be of degree p. If you evaluate that, you have diagonal a minus lambda everywhere, and the coefficient, the largest power of lambda would turn out to be minus lambda to the power p. Okay, and there's nothing multiplying this. The rest of the powers of lambda will be all lesser. The other powers of lambda will be all lesser. So the coefficient of lambda to the power p is actually minus 1 to the power p. It is non-zero, and there is no other higher power of lambda possible, because there are p rows. If you take a determinant, you have lambda, every row has one lambda there, one term with lambda. So if you have p rows, okay, the maximum power of lambda that you will get by making various kinds of products will be lambda to the power p, okay, at most. And that too, if you work out, it will be minus, the coefficient will be minus 1 to the power p, which is non-zero. That's all what we want. So Cp is non-zero, and there won't be any higher power of lambda. So the degree of this polynomial with numbers, coefficients, this is p. So degree of this polynomial is p. Okay. So Cp is non-zero. That's all I will say. It's minus 1 to the power p, but the way I define my characteristic polynomial is determinant of a minus lambda I. Some people do it lambda I minus a, in which case their Cp turns out to be 1 always. But in my case, Cp will be minus 1 to the power p. But in any case, that doesn't matter. It should be non-zero. That's all. Okay. So, so this is the characteristic polynomial. These coefficients depend upon how this a has been structured. Okay. All right. Now, what about this? This will be horrendously complicated if you actually try to evaluate this. But here is where the matrix, the polynomials with matrix coefficients come in handy. You see this whole matrix? It consists of cofactors. Each cofactor can have a maximum power of lambda with p minus 1. Okay. You remove an element, Suppose you don't remove a diagonal element, doesn't matter, you remove a diagonal element, doesn't matter, you will be left with p minus 1 by p minus 1 submatrix. Now how many terms with lambda can it at most contain? P minus 1. Okay. So the entries, each one of them would be having p minus 1 as okay. So many cofactors has this kind of a structure. It's horrendously complicated to actually evaluate this based on the fact that this is a cofactor adjoint. So let us invoke the idea that we have previously. You work with the ring of it's a ring, but just let me call it a set. The set of polynomials of in lambda with matrix coefficients, p by p matrix coefficients, along with 0 null matrix. If you think of this as a member of that, this is indeed a member of that. All said and done, what you get at the end by evaluating this is certainly a polynomial lambda with matrix coefficients. If you work out the cofactor, this turns out to be a polynomial. So this is a member of S. This is a member of S. It will at the end of the day turn out to be a polynomial in lambda with matrix coefficients, p by p matrix coefficients. It has to. So this is what you observe. This is an observation. This is a member of S. This certainly is a member of S, as you can see. Call this P of lambda, call this Q of lambda. Good. P of lambda, Q of lambda. What do you have on the right? On the right, we have a very simple member of S. It simply consists of lambda to the power p into some multiple of the identity matrix plus lambda to the power p minus 1 into some multiple of the identity matrix. So let me write this down. So a minus lambda times identity into b0 lambda to the power 0 plus b1 lambda to the power 1, or you could write this as lambda 0 b0 or lambda 1 b to the power 1. I don't worry about how you write down because lambda is a scalar, you could take it here or there inside. So plus dot 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 plus, and now I have to be careful. This, if not 0, should have a degree. So let me call this bq. I am not sure what degree this would be at this stage. I am not sure what it is. So let me call it some q, where bq is not equal to 0, null matrix. Some q is there. And on the right, what do you have? I simplify this expression, put this thing inside. You simply have this expression, I equal to 0 to p ci times identity. I take this together purposely and say lambda to the power I. So ci is diagonal, ci for each I. So this is a polynomial of degree p because the last cp is not 0, minus 1 to power p in my case. So it's certainly not 0, and there's nothing higher than p displayed here in terms of powers of lambda. So it's very clear that the degree of this polynomial is p, certainly. What is there on the left? The degree of this polynomial is 1. So degree of this p of lambda is 1. Degree of this q of lambda, capital Q of lambda, is small q. And degree of this is small p. Okay. So we have the result. Degree of I hope I had wrote it properly last time. I think I should have written this. Degree, I recall degree of p of lambda times q of lambda is less than degree of p of lambda plus degree of q of lambda. I hope I wrote it right. So recall. So pretend that this is P of lambda, this is Q of lambda. So degree of the product, which is this, P, small p, less than or equal to 1 plus Q. Okay. So therefore, you have P minus 1 is lesser than or equal to Q directly from here. Okay. So Q could be at best at least P minus 1. It could be P as it stands from the reasoning we have done carried out. It could be bigger than P, it could be P, it could be bigger than P, but certainly it has to be at least P minus 1, okay, which is what you could expect like ordinary polynomial division. Okay. So Q should be at least P minus 1. So this is what we have, first result. All right. So this is a very quick way. Instead of working out with all the cofactors and try to figure out things, you could do it this way. That's a complicated way, but this is you could still do it that way. But here you have this result in a more concise form, and moreover we have learned more about abstract structures. Okay, so now let me call this what should I call this, equation 1 or something. Okay, let me call this equation 1. Equation 1. Cp is not 0. Okay. Let us try to simplify this equation and see what you get. So simplifying equation 1, we obtain the following. You could either work out things like this, but let me put this as a summation over I equal to 0 to Q. That's easy. So we get A minus lambda times identity sigma over I equal to 0 to Q bi lambda to the power I equals sigma over I equal to 0 to P Ci times identity into lambda to the power I. This will remain the same mostly throughout. Let us get this straightened out. Therefore, I multiply. We have seen that this distributes from the right. This is dot. So this is also dot. So that distributes from the right. Dot distributes on the right over. And minus lambda times identity is the additive inverse of lambda times identity. So I assume that result. So A bi. So let me put that summation sign there. Sigma over I equal to 0 to Q abi times lambda to the power I minus sigma over I equal to 0 to Q bi, and I take that lambda inside, I'll get lambda to the power I plus 1 equal to sigma over I equal to 0 to P Ci times identity lambda to the power I. As you can see, if we were to put all the lambda to the power same powers and the coefficients of matrix coefficients all together for the same power and list the powers one after the other. If you want to do this, you better have the same index on both sides. So let me think of this as a single index. Instead of I plus 1, I could call it K or J or M or something like that. M is being used, M is not used. Okay, you call it small m also. Okay, so you could use that. So let me call I plus 1 as J, I equal to 0 to Q A B I lambda to the power I minus B lambda to the power J. So I've decided to call I plus 1 as J here. If I plus 1 is J, then in that wherever I apply that, I would be j minus 1. I have b high here in the same term, then that I would be j minus 1. So I have j minus 1. I have an I appearing here also, so that I would again be j minus 1. So let me, so j minus 1 goes from 0 to q. It was I earlier. That turns out to be sigma over I equal to 0 to p ci identity lambda to the power I. Okay. So let me simplify this a little further. Sigma I equal to 0 to q abi lambda to the power I minus sigma over j. J minus 1 is 0. If j minus 1 is 0, then j is 1. And if j minus 1 is q, then j is equal to q plus 1. Okay. And then this is bj minus 1, lambda to the power j equal to sigma over I equal to 0 to p ci times identity lambda to the power I. And now I have the same index, a single index lambda to the power something, and now I want to take this together. So I better call them by the common name. Call both of them k, or both of them as I, or both of them as j, something like that. So let me call this I. So now this j is now called I, a new index. So this will be sigma over I equal to 0 to q abi lambda to the power I. You could use k here, bk, and then say minus I equal to 1 to I equal to q minus plus 1. This I is different from this I. Okay, so it's possible. You could call it k, and then call the whole thing as I. It's possible. So this could say k going from 1 to k equal to q plus 1. Bi minus 1 or k minus 1 lambda to the power I, lambda to the power k equal to sigma over I equal to 0 to p ci times identity lambda to the power I. And now here lambda to the power I, lambda to the power k, lambda to the power k on both sides. You can take those terms together. But at the same time, you must remember something. The summation is being carried out over a different range. This is from 0 to q. In this case, it's from 1 to q plus 1. Okay. So let me make things easier for us. This has an extra 0 term. Let me write it separately. So I have ab0 lambda to the power 0. I need not have written that lambda to the power 0 plus sigma equal to sigma from I equal to 1 to q, since I have written down the 0 term separately, abi lambda to the power I, minus, you will see you have an extra q plus 1 here. You have a q term and a q plus 1 term, which is not there here. So let me list that q plus 1 term separately. Okay. So sigma over I equal to 1 to q b I minus 1 lambda to the power I, and I have to put a minus sign, b I equal to q plus 1. So this is q plus 1 minus 1. So let me write down q plus 1 minus 1. Okay. Lambda to the power q plus 1. I was q plus 1. And then of course this whole thing is sigma over I equal to 0 to p ci times identity lambda to the power I. So far so good. And now what have you? You have these ranges the same at the cost of checking out a few terms. And so I can take these things together. So let me simplify. Therefore, ab0 lambda to the power 0 plus sigma over I equal to 1 to q abi minus bi minus 1 lambda to the power I, and of course you have this extra term b q minus 1, q plus 1 minus 1. Let me simplify that. That will be q bq lambda to the power q plus 1 equal to sigma over I equal to 0 to p ci times identity lambda to the power I. Okay. So far so good. So now here comes an issue. You have two polynomials in lambda with matrix coefficients on both sides. Those who have been doing undergraduate applied mathematics you'll automatically equate powers on both sides. But in abstract things have to be reasoned out carefully. If you have two polynomials like this, p of lambda equal to q of lambda, capital Q of lambda, capital P of lambda is the same as capital Q of lambda, and you can take one on the other side and then add or subtract the coefficients. The whole thing will be in null matrix. Okay. We demand that this works for all lambda. Then you would have each coefficient to be the null matrix. Okay, that means the corresponding coefficients are equal on both sides. So this has to be reasoned out. It's not simply obvious that you equate coefficients on both sides. Although we will be doing it here, this comes from the concept that S is a group under polynomial addition. So you can show that when you show that it's a group, you will automatically get this result out. So I'm assuming that here. Ordinarily, when people do applied mathematics, they generally don't bother. They say, oh, just equate parts on both sides. Okay, so that has to be reasoned carefully. In this case, it goes through. So I equate the coefficients of powers of lambda, the same powers of lambda on both sides. So let's see what happens. Now I have faced the problem. I still don't know what is q. I know certainly that q is bigger than p minus 1, bigger than or equal to p minus 1. So what would happen if q is bigger than p minus 1? If q is strictly, small q is strictly bigger than p minus 1, then what would happen? Then LHS has lambda to the power p q plus 1. As the largest power of lambda on display. There is nothing more on display here. This q. And the coefficient, what can you say about the coefficient? Its coefficient is minus bq that means bp minus 1 minus bq. No, sorry, bp minus 1. That is its coefficient. So this coefficient happens to be, this is bq, okay, and the polynomial is so constructed that it's a coefficient of lambda to the power q plus 1. It so happens that way. Okay, in this case, this is not b. This is something multiplied to b, pre-multiplied to b. That's why you're getting this. So bq is not the coefficient lambda to the power q. It would have been if I was talking of b matrix or that adjoint term matrix. It's not that. I'm talking of this product. So therefore you're getting this. So its coefficient is bq. Is it 0, non-zero? Recall, you were worried about this polynomial, and I chose this q in such a way that it's the degree of this polynomial. So bq better be non-zero. If bq is not equal to 0, minus bq is also not equal to 0. I think I made a mistake here. If q is bigger than p minus 1, so this should be okay. So I'm sorry. So the LHS has lambda to the power q minus 1. Let me. This is not lambda to the power p. I'm sorry. Let me call this lambda to the power q plus 1. I'm sorry. I'm sorry for this. I wanted to say q is bigger than p plus 1, p minus 1. And LHS is lambda to the power q minus 1 as the largest power. Its coefficient is this. It's non-zero. And q is bigger than p minus 1. So lambda to the power q plus 1 has a non-zero coefficient. Okay, and there's nothing more on display. So this is certainly the largest power of I think I need not have this. Okay, sorry, I need not have this cube bigger than p minus when I say this. Let me just erase this part. Sorry, let me just erase this part. LHS. Sorry, let me begin again from this stage. The left hand side has lambda to the power q plus 1 as the largest power of lambda on display. Its coefficient is minus bq, which is not equal to 0. And so the degree of LHS is certainly q plus 1. Therefore, degree of LHS is equal to q plus 1. This is for sure. I have not invoked that q is bigger than p minus 1 this far. I erase that. Okay. Now I invoke it. Now I say the degree of LHS is q plus 1, and I know that q happen to be bigger than or equal to p minus 1. Therefore, degree of LHS equal to q plus 1, and q is bigger than or equal to p minus 1. Therefore, this is bigger than or equal to p. Okay. So, degree of LHS is bigger than or equal to p. This is what you obtain. All along you have the right side. What is the degree of right side? It's precisely p. But degree of RHS is exactly equal to p. Okay. Cp is non-zero. In my case, it's minus 1 to the power p. It's very clearly non-zero. So Cp times identity is a non-null matrix, and lambda to the power p is the largest power of lambda on display here. So you have these two sides, and so if these two are equal, then of course, if this is bigger than p, the degree of LHS is bigger than p, there will be some coefficients of lambda to the power p plus 1, p plus 2, and then nothing on right to equate to. For all this works for all lambda. And since we say everything on both sides the coefficients should be equal, then automatically the higher the coefficients of powers of lambda higher than p would have to be 0. So that can't happen. So this cannot happen unless you have this exactly equal to p. Therefore, degree of LHS will have to be equal to q plus 1, which is have to be equal to p. It can't be bigger than p. So this inequality, the bigger part is, I should have said this is not greater than p, not greater than p, not greater than p. So if it is not greater than p, because of this result, you will get to be equal to p. So therefore, you will have q plus 1 equals p. Therefore, q plus 1 equals p, or q equal to p minus 1. Much like your ordinary polynomial division, this is q minus 1, p minus 1. So that's what you know now. This is p minus 1. So from this equation, you have q equal to p minus 1. So let's come back to this equation, and now you don't have any extra terms in lambda hanging around on either any of these sides. So let us go back to the equation and see what happens. So equating coefficients of lambda on both sides, of identical powers of lambda on both sides. I told you this is a non-trivial step, but we'll go about it assuming that you have shown results when you try to prove that S is an abelian group or just a group. Equating coefficients of identical powers of lambda on both sides of equation, let me call this 2. equation 2, we obtain, what do you obtain? Let us try to see. A b 0, there is nothing, no lambda to the power 0 here, would be C0 times identity. Then you have this big thing, okay, and you are going up to q. Q is p minus 1, okay. So you simply have a b I minus b I minus 1 equal to C I times identity, where I equal to 1 comma 2 comma whatever that is, comma p minus 1. Now, moment I do these things like I 2 etc. See, it might happen that this might end at 1, okay, but I assume that you understand. P minus 1. So this is what would happen, because q is p minus 1 for us now. And then finally you have minus bq, which is the coefficient of lambda to the power q plus 1 or lambda to the power p, simply Cp times identity. Okay. So you have 3 sort of equations. This is many equations here, but into 3 types. Okay. And now this is sort of what you get from the equation, that's all. Now you are going to proceed towards Hamilton-Caley theorem, or Caley-Hamilton theorem. And what you have here are simply these coefficients which have come from the characteristic polynomial of A. So they contain all the information about the characteristic polynomial of A that could be implemented in lambda or in A or in any other thing, okay. So the information about the characteristic polynomial is already in place, you have, and for free you got it multiplied by an identity matrix, a p by p matrix. It is identity, very nice actually, very useful, but note that you have a matrix on the side and a matrix on the left. Now I cheat you a little bit. From here I try to construct the polynomial, the characteristic polynomial of A in A, by noting that if I multiply the first equation by a to the power 0, all these by a to the power I respectively, this by a to the power p, and adding all the result together, okay, I will get the characteristic polynomial of A in A on the right, okay. So I multiply by some power of A in each of these equations. It's nice if I multiply by right, things will still hold. A b 0 into a to the power 0, a bi into a to the power I, bq into a to the power p. This is what I would get, but that turns out to be not so useful. Instead, I imagine that I pre-multiply this by a to the power 0. I pre-multiply this by a to the power I pre-multiply this by a to the power p. Then you get something interesting. So you see, when you work things creatively, you might come up with an approach that leads you to something which is not wrong. See, my post multiplying by a to the power 0 or a to the power I here is not wrong, okay. If you multiply that and add on the right, also you will get the characteristic polynomial. You might get something on the left which is useful for something, okay, something else. That's possible, it's not wrong, but it may not be useful for you for what you started out to do. So if you think a little bit creative, there are other things you could do. You could pre-multiply and see what happens. So if you pre-multiply, let me do that. So pre-multiplying, so here I pre-multiply by a to the power 0. Here you pre-multiply by a to the power I for each I, and here you pre-multiply by a to the power p. Remember, this is bq, which is p minus 1 now. Now we have shown that this p minus 1. So let's see what happens. I add the whole thing. Let's see. So I would get AB0 plus sigma over I equal to 1 to p minus 1 a to the power p, sorry, a to the power I multiplied to a bi minus bi minus 1 minus a to the power p bq, and since, okay, let me write this q, let me write this p minus 1 because q is p minus 1. This equal to sigma over I equal to 0 to p ci times identity lambda to the power I. Okay. So in fact, what you have on the right is the characteristic polynomial of a in A. So I will keep this as it is. So let us see what happens here. Therefore, a b0, again I try to do similar things, but there is no lambda here now. You have sigma over I equal to 1 to p minus 1 a to the power I plus 1 bi minus sigma over I equal to 1 to p minus 1 a to the power I bi minus 1 minus a to the power p b p minus 1 equal to sigma over I equal to 0 to p ci I identity into lambda to the power I, and I try to process this further. Again, I wish to compare these two. Note that there is a power of a here and one lesser than this power. Power of a and one lesser than this power. So potentially I could compare these two with the same index, suitably manipulated. So let me do the following. I have this a plus 1, I plus 1. Let me call this I plus 1 as j, as I did previously. So again, you have this as a b0 plus sigma. If I were to call this as j, so then j would be I plus 1, or I would be j minus 1. So bi would be b j minus 1. I is j minus 1, so j minus 1 goes from 1, j minus 1 equal to p minus 1. Okay. And this, let me keep it as it is, 1 to p minus 1, and a I b I minus 1 minus a to the power p b p minus 1. Okay. And this is the characteristic polynomial of a in A. Okay. Now let me simplify this a bit. Therefore, a b0 plus j equal to j minus 1 goes from 1. If it is 1, then j is 2. That is j is 1 plus 1 is 2. And if j minus 1 is p minus 1, cancelling minus 1 on both sides, you have j equal to p. So let me write this p. J goes from 2 to p. aj bj minus 1 minus sigma over I equal to 1 to p minus 1 ai bi minus 1 minus p a to the power p bp minus 1 equal to characteristic polynomial of a in A. Oh sorry, I think I made a mistake. This should be, sorry, not lambda, but it should be characteristic polynomial of a in A. So this will be a to the power I. I am sorry. I am sorry. I kept on writing lambda by habit. I am sorry. This is a to the power I. Everywhere you need to make the change. Please make those changes in your notes. This is not lambda, but a to the power I. A to the power I. Okay. So when I multiply by a to the power on both sides, what you have on the right is the characteristic polynomial of A in A. Okay, now we are in business. And now I look at this. This is J. I could call this J, or both of them as K, or things like that. Let me call this I. So instead of J, I have this I, sigma over I equal to 2 to P AI BI minus 1 minus sigma over I equal to 1 to P minus 1 AI BI minus 1 minus A to the power P BP minus 1 is equal to sigma over I equal to 0 to P CI times identity into lambda to the power I. Actually, you could need not write this identity. You could simply say Ci A to the power I. Since I had that mistake of lambda, I was doing this. Okay, so if you want, I can just make this change here. Okay. And now what have you, if you look at, we engineered all this, okay, so that you get the summed, the term in the summation equal on both sides or comparable. And here you have AI BI minus 1, AI BI minus 1. I would like to take things together and cancel them out, but we have to be careful, the range is different. So we use the same trick, we just take out whatever is extra on each side, trying to figure out something common, maximum common things. So you say I goes from 2, no problem. The P, this goes to P minus 1, there's 2 and 1 here, so we'll keep the bigger one, 2. P and P minus 1, we'll keep the smaller one, P minus 1, and check out this extra term separately. So you have A B0 and plus A to the power P BP minus 1 and plus sigma over I equal to 2 to P minus 1 A to the power I BI minus 1 minus sigma. And now this I is 1, I need to check out this lower thing. I wanted to start from the summation, the bigger of the two to the smaller of the two. So I equal to 2 to P minus 1 AI BI minus 1, and the leftover, which is simply minus A to the power 1 B0. And I had this B A to the power P BP minus 1 all along is equal to, I am running out of space, let me make some space for myself. This will simply turn out to be sigma over I equal to 0 to P Ci A to the power I. Okay, that's a characteristic polynomial of A in A. And now I can take these together, and you'll see what you get. You have AB0 plus A to the power P BP minus 1 plus sigma over I equal to 2 to P minus 1 A to the power I BI minus 1 minus A to the power I BI minus 1 together, and some extra terms, A to the power 1 B0 minus A to the power P B P minus 1 is equal to characteristic polynomial of A in A. Okay, and you see what you get, A to the power 1, here this cancels with this, so does this, and this cancels with this for all I. So what you get is simply 0 matrix P by P is equal to characteristic polynomial of A in A. Okay. So if you have any matrix A, you construct the characteristic polynomial of A in A, it should evaluate to the null matrix. This completes the proof of Caley-Hamilton theorem. Thank you.